let's finish up these slides. Computer risks and bugs. We'll learn some very sad things, right? Unfortunately, about computer science. And we figured out that there's a way to gain more confidence in our programs. If we just test those things, then we can be pretty happy. If we write enough tests, at least, we can be pretty confident that our programs are going to do the right thing. There is another side to that, which I said once. So testing is what I showed you last time. There's another topic called verification, which is like once and for all. It's better, it's stronger than testing, but it's harder. All right. So there are ways to make sure that your programs are correct from the start. You cannot have any bugs, even without making any tests. You don't even need to make tests. All right. So here's a few ways. So one way to make a piece of software that is automatically correct is to just like make two versions of that same piece of software, have two groups work on the same program, and they can check each other's outputs, right? You give them the same input, they'll check each other's outputs, which is really nice. And then like hopefully they always agree, but if they don't, then that raises an alarm and somebody like a human has to step in. Like that's a good idea, yeah. That's not bad. There's that, and then like there's the idea of mathematically proving that your program is going to do the right thing. So that lets you not have to write any tests at all, just saying that, okay, yeah, my program's never going to do anything wrong, and I will prove that to you without having to write tests. So here's like an example proof. So here's some quick Python code on the slide. Let me fix these real quick. There we go. So notice that if I say this, right, x equals 42, and then x equals x plus 1 in Python, you know what's true here, right? You can prove, right, to yourself. It's pretty easy to imagine that x is definitely going to be 43 here. Does that make sense? Without a doubt, x will be 43 the second you get after those two lines. And so you can kind of do the same thing for everything in Python. You can prove what it means to run a line. Going to happen if I give this input, what's the output that's going to be produced, and like you can mathematically prove that it's always going to be the correct output. So you can kind of imagine that that's going to happen. So that's like the hardest core of thing that you can do to make sure your program's always going to be correct. Just make a proof for it. Represent in math what's going to happen in your code, which is really nice. There's something a little bit not as fancy called an analyzer. Program analysis is something I studied in grad school, and it's essentially the same idea, but you can do slightly fewer things with it. It's like you're running the program in math, and you're like seeing is it going to do the right thing? So like an analyzer could do this as well as a proof. They could do both of those things, which is really, really nice, and you can make sure like one does the other. So proofs and analyzer, they kind of go hand in hand. You prove that your analyzer is correct in a sense. So those are ways to just like make sure that your program's always going to be right. It's a very, very complicated topic, though. You'll have to wait till grad school to learn a little bit more, probably. But there's that. There's also ways to specify like what the program should do in a way that everybody understands, because we all know that English sucks for those ideas. So like there's some specification languages. There's one good example called, it's not called Z, it's called Z, because it's from Europe. And it's like when you specify what your program should do, you're like saying, you're not giving the algorithm, you're saying what should happen now. So like you say what should be done, and then you use some other programming language or some other method to like prove that you did those things. So like here's an example requirement. Here's the specification for a program, like the output. The output should always be greater than or equal to 42, and like that's something that you could put into a specification language and analyze and prove that your program's always going to be right. So like this program meets that specification. Okay, but yeah, those are ways to make the correct software. There's a way to like prove that your program is correct with some other, like there's another programming language which is fun to think about. One of the most popular ones is called it's a French term, so it means rooster. So like the Coq proof assistant, I guess is how you pronounce it. So that's something I studied. It's just fun. It's cool ideas. I'm not going to test you on any of them, of course, though, because it's a little too complicated. But these are things that people do, all right? But there is a problem to this approach, just like there might be a problem to testing as well, because all of these ideas, all these ways to make sure your program is correct, is for you to know up front what your program should be doing, right? And that's easier said than done. You have to know exactly what your program have to specify exactly what your program should be doing, all the ways that it could perform, all right? And we might get that wrong, or we might not know enough, which is a problem. And then at the end of the day, like if you write down your specification wrong and you write a correct program with respect to that wrong specification, you still have a wrong program at the end of the day. Like maybe it should have been output should have been always greater than 52 or something. But in theory, this makes things slightly more correct. All right, so there are ways to do this kind of stuff. And this is for like the hardcore stuff that you need to be correct, like autopilot software and stuff like that. Okay, so yeah, let's talk about planes because this is very important. All right, so when you are in a plane, your pilots are talking to the air traffic controllers, or ATC. I like to listen sometimes, like there's YouTube recordings of people talking to ATC. It's kind of fun to watch what they're doing. But there's a little box inside of every plane these days called the Traffic Collision Avoidance System. It's called TCAS, or TCAS for short. And what it does is there's little receivers, senders and receivers in each little box that's in every plane. And it can just tell like if planes are too close to each other and they're about to hit each other. And it tells the pilots like what they should do to avoid a collision because those planes are getting way too close. So like here's one plane, my best artist rendition of a plane, and here's my best rendition of another plane that might be a little too close and might be crashing into the first one. The TCAS system will notice that they're too close in the same level of altitude and will tell one to like pull up and one to like go down. And that's how they'll avoid their conflict. So unfortunately, the first versions of the TCAS system were not too good. Like the planes were really far apart. It told them that they were still going to crash, and so everybody like stopped kind of listening to that system. Unfortunately, so kind of cried wolf. Okay, but eventually it got really good, and like it was like it's only going to set off an alarm if the planes are really too close, and everybody should pay attention. But unfortunately, two planes really did crash when one pilot, they trusted the TCAS, they did the pull up or whatever it told them to do, and the other pilot ignored it, and like they were talking to the air traffic controller, and they said to do the same thing that the other pilot was being told to do by the box. So like, they were supposed to like go down, but they went back up as well. So that's really unfortunate, and they ended up crashing because not everybody paid attention to the box. And so now it's a fun idea to think about, like we are in the skies, the like boxes are in control of us because there's a law now. Everybody has to disobey a human. You must obey the box instead now. And that will prevent all the crashes. Everybody has to disobey the air traffic controllers and trust the TCAS system. Which is wild, right? You're putting your life in the hands of a machine in a sense. What do we think about that? It's a little weird. So I'm going to force you to have an opinion right now. All right? So I would like you to get into peer instruction groups, please, with the people sitting next to you. And I'll stop attendance after this is done. But that's a great example, right, of something that we may have not known about. So let's go to the written nice page, and you can elect a leader. I'll force you to think about both ideas. Though, like, here's your question: do we depend on computers too much? Like in the skies, even we're forced to depend on computers. It's a law to do that for our own safety. I'd like you to write one argument saying, yes, we do depend on computers too much, and here's why. And then another argument against, and saying, like, no, actually, we don't depend on computers too much, or maybe not even enough. We should depend on computers more, and also tell me why. Okay? Does that make sense? So yeah, take a few minutes to try to unpack those ideas together, and we'll come back and discuss. time. You had some good thoughts. A couple more minutes. All right. Was that enough time to get something in there? One of the two groups. I'll give you 1 minute to finish typing and press submit. Oh, nice. Perfect. Let's see here. Yeah, I heard some very good thoughts. Oops, did not mean to do that. So I'm excited to see what you say. Like, obviously, I'm sure like one of these ones are what you really believe. I forced you to think of the other way too, but nice. All right, group 51. We depend on them too much because we're depending on them more than people. Maybe we should trust people more. That kind of makes sense, right? Places like fast food. Yeah, I've seen. Have you all seen the funny videos of like people saying, "I would like 8,000 water cups to just get access to a human because they don't like talking to the AI." That's funny. Yeah, we rely on our phones every day. When the I think what you're implying is that like we should be talking to other humans and those are the people who we really should trust. Yeah, that makes sense to me. And then why might we not trust computers, or why might we not depend on them too much? Ethical and moral issues decided by humans, like political decisions. Ooh, nice. Yeah, so it's hard for humans to make decisions that are it's sometimes hard for humans to be rational, right? Depends on the situation. And a computer is more like, all right, just follows the rules. Like maybe they should be making our decisions, just like this TCOS system for the airplanes. That's a great thought. I like that. I like that a lot. All right, nice. What about Group 52? Our entire infrastructure, like power grid and everything it provides, is a major issue if we are unable to keep it operational. So that's 4. Depending on them too much. Like maybe we should have backup systems that are like human powered. Is that kind of what we're saying? Makes sense to me. Nice. Yeah. And then a reason why we might need computers a little bit more, we don't depend on them enough, is we still have to lay down the foundations of whatever we are attempting. Without us, nothing would come to fruition. So, like, at the end of the day, there's still going to be a human involved, is kind of what you're saying. That's true. So there's potential for it to do even more for us. Very nice. Awesome. These are great thoughts, you guys. Very good. Very nice. Thank you for those. Yeah, those all make a lot of sense to me. I'm glad that I'm forcing you to think potentially in a different way that you might really think. But here's some ideas that I wrote down. Like maybe with that air traffic example, like maybe we should be following the box always. Like we should be trusting the computers because like they're all going to make sure that everything is working out for us. All right. But yeah, like maybe we should just throw away all the computers. Let's ask Kant and Mill what would they think about this question. Like Kant would ask a question something like this, right? He'd be like, should we always be looking to computers to solve our issues and our problems? And he's of course a huge proponent of individual rights. He's like, yeah, if you just want to go live in a log cabin and never use a computer, like that's totally fine, dude. So I think Kant would be like maybe saying that like we're fine, we don't have to worry if we don't want to. Like computers are not necessary in anyone's life. But Mill would probably say something like, yeah, we should like everybody needs a computer because this is how we like make sure that everybody's like happy and their lives can be improved and they can work remotely and go to class online and stuff like that. Like their lives will be better if only they had more computers. Right? If only we gave everybody a computer or something. So yeah, that's kind of how I might break it down to have these famous people approach the problem. And again, it's just a viewpoint, right? Just a way to help you consider your own answers to the dilemma. Yeah. And there's plenty of ways, right, that computers help make us safe. Ways that you couldn't really have if we got rid of these features that I'm about to talk about, right? Cars, every car made after some year that's like in the 90s, right, has the anti-lock brake system, and that helps you stop sooner and not kill people as much, which is important. And then check engine lights. Just imagine like those didn't exist and like your engine just suddenly blows up and you didn't know what was wrong, right? You didn't hear something. So like computers are definitely helping us and keeping us safe in a lot of different ways. Airplanes have that TCOS system to make sure they don't crash into each other. They also have autopilot to make sure like that the pilots can like take a little break so that like they can come back when they're needed when like, the plane needs to land and stuff. That's really nice. And then like you can imagine like everybody is like buying into like those Ring cameras and like home security systems and stuff like that. And that like helps deter thieves and stuff like that. You can imagine. I think back before electronics, everybody had to go buy a dog, right? That was your home security system, I guess. Yeah, what else? Like phones, you're storing so much personal information. Like phones are also a problem, but we have a solution that's like lock them, right? Give them a passcode. So maybe that's not a good example. But there's also online banking, which is very nice and convenient, and with the power of our password and two-factor authentication, like nobody's going to get in to our accounts. Only we are. Okay, so that's pretty nice. So I'm very biased, of course, but you can imagine that computers are doing pretty well for us these days, or at least we think. Okay, so yeah, that's what I wanted to say for these slides, and I want to start some new ones. I would like to talk now about artificial intelligence, a very hot topic. I think you would hopefully have been looking forward to this. So there's a lot of cool stuff going on. Computers are very, very smart. Let's talk about it. All right. So first, I want to talk about computers and how nice and quick they are able to do our computations for us. There's something called Moore's law that I want to teach you about if you haven't heard of it before. All right, it's going to answer this question: how fast are computers getting faster? Okay, it's a weird question to ask, but it's a fun one. There's like a really cool Wikipedia page with a fun graph that I stole that you can go back to if you want to know more. But Moore's law is named after a man, Gordon Moore, who was the co-founder of Intel, which is a very, very important company, right, in computers these days. So he just observed back in the 60s, I think, that, okay, the number of transistors, you remember what those are? The number of transistors in a chip, in like a CPU, is doubling. It seems to double every 2 years or so. All right. Oops, this one messed up the pens as well. So he noticed that, okay, every time we wait a year, like our engineers at Intel are figuring out how to double the number of transistors, right? So let's see here. Year 1, there was 1 transistor. Year 2, now we have 2 transistors. Year 3, we have 4 transistors. Year 4, we have like 8, right? Way up here, 8. 1, 2, 4, 8. It's exponential growth. And he's like, I think that's going to keep going like that. And that was just what he thought, okay? And it ended up being true for decades. The number of transistors on a chip is doubling every 2 years, and transistors are involved, like the nitty-gritty details. Transistors, those make the logic gates that we talked about, the ands and ors and things that build computers. So if you can shove more of those inside of a chip, then you can make more processing power in your computers too. And so for a long time, this meant that computers, just wait 2 years, I guess. Wait 2 years. They'll get twice as fast, and we could run our same program and it'll run twice as fast, which is beautiful. But sadly, that's not so true anymore. The number of transistors is still pretty much doubling every about 2 years, these days even. So it's been true since the 60s, but they're not getting twice as fast anymore. Every CPU is essentially, unless you use liquid nitrogen or something, they are tapping out at about 4 gigahertz. Have we seen that? These words before? Suffixes and things. This just means that the computer can process 4 billion things a second. Giga means billion. So about 4 billion operations a second are what CPUs can do these days. Right? But the reason we couldn't go any faster is because we started running into issues with power limits. You can't shove electrons into a CPU and keep it cool very well once you make it faster than this, which is interesting to think about. All right. So that's when everybody decided, okay, if we can't do it that way, if we can't make computers faster by just making their speed faster, we're going to put a bunch of mini computers in a computer. So that's when multi-core CPUs became a thing. So nowadays what you do when you buy a laptop or whatever, you put a bunch of independent CPUs on your chip, okay? And so maybe you have a 4-core processor inside of your laptop or something, and each processor is running at 2.5 gigahertz, and so they can run 4 separate programs all at once, which is really nice. Okay, that's pretty cool. And we're soon enough, Moore's law is going to stop working. It's working pretty well still, but it's tapering off. I would say we're eventually going to hit an atomic wall, because you can only make transistors so small before you get you start running into weird quantum effects. You can only put so many electrons in something that tiny, and you have to worry about quantum issues. But yeah, it's been going pretty well for us so far. So highly encourage you to visit this Wikipedia page or look on YouTube to know more. But here's a wonderful graph of this idea. And, let me explain it to you. So here on the x-axis we have years. Conveniently, incrementing by 2. All right, back to the 70s, all the way to mostly present day. And then on the y-axis, we have the number of transistors, and each point is going to have a CPU. And this y-axis is increasing logarithmically. So if you remember what that means, if you see a trend line, and we do, if it's a logarithmic y-axis, that means it's really an exponential trend. Okay, that's the goal there. And so yeah, we really do see a line there. That's pretty nice. And what does that mean for us? Let me draw my best line. Cool. So let's talk about the good old days for a second. Whee! Yeah, some of the first Intel processors, they didn't even have 5,000 transistors. Crazy. You could still do something though back then. Motorola 6800s, I think that was one of the ones in the first Macs or something. That or one of the first game consoles. I can't remember. They used to be a huge player in the CPU game. Still under 10,000 transistors, but it kept slowly growing, right? Doubling and doubling and doubling. Eventually, Intel processors had like 20,000 transistors, and they were a few times as fast as the ones in the 70s, which is really cool to think about, all right? Isn't that fun? Let's see what we got. And then at the same time as Intel processors, they're having making their way to a million transistors. You have the ARM processors. You've heard of those? I think I said it once upon a time. But everybody's phone and new Macs and stuff, and even game consoles these days are using ARM processors because they're nice and power efficient, but still just as fast as the ones that are in desktop computers, which is really fun to think about. So you see these, this Intel processor had almost 500,000 transistors, but these ARM processors had not even 50,000, 10 times less, but they were competing at the same time. Just as cool, just as fast. A competing idea, which is fun to think about. And so that's why they won out for phones because of their power usage. But yeah, that's pretty exciting. Then we come to the early 90s. We have the Pentium processors, which I remember back in the day, starting to get over the million count of transistors, and we're still doubling. These are single core processors still. No multi-core exists yet, and at least in consumer hardware. Getting twice as fast every 2 years, twice as fast. And then by the time we get to this Pentium 4, we tap out of that 4 gigahertz speed limit, and that is about 50 million transistors, which is fun to think about. And then we notice, okay, we got to go faster. We need to shove more transistors into our chips. And so we start, see the word core appear. And so, okay, we're going to put 2 cores, 2 separate CPUs on our chips. And they'll be able to run 2 programs at once. And so we can still double the number of transistors, but it's not doubling the speed anymore. You can run 2 programs at 4 gigahertz, essentially. And that brings us to the millions of transistors. And if you're going to build a server, you're going to make 32 core, 72 core processors, and we're making our way slowly but surely to almost 100 billion transistors. Crazy. A fun time had by all. Does that make sense? Have we heard of this idea, Moore's Law, before? It was really cool to think about. So one day it'll stop working, but it's still going for now. Yeah. 28 billion? That's impressive. And how many cores does that have these days? Is it 8? Or more than that? Maybe 16. But yeah, that's really exciting to think. Nice. Okay. It'll just keep getting bigger and bigger, but one day we'll kind of max out, and maybe we'll just have to we can put a bunch of cores inside of a computer, but that takes up a lot of space. So one day it'll get as big as it can be to shove inside of a laptop, maybe, but we're still working on it. Cool. So yeah, and so it used to be that you just wait around for a few years, your programs get faster, and that's not really true anymore. Now you need to make a multi-core efficient on multiple cores at once. But that brings us now to artificial intelligence, because computers are fast enough to actually do things like interpret our speech and generate images and help us cheat on all our homework assignments. I hope we're not doing that. But yeah, let's talk about what is artificial intelligence. What does that all mean together? Like, it's going to answer these questions. Like, how do computers think? How do we program them to think kind of like a human, right? And how do they get so good? Like, what do we do? How does it all work? So I'll give you probably not entirely today, but next time as well. We'll talk about it a little bit. How does artificial intelligence actually work? And so that's an exciting thing that you get to learn. But we should define what it means first. What does it mean for artificial intelligence to exist? It's just like, all right, intelligence artificially. It's kind of self-explanatory in a sense. It's like, all right, you got a machine, we're teaching it to think like a human might think, right? And so what does it mean for a human to think? We get philosophical all over again, don't we? So, well, we think because we're perceiving our environment. We've got senses, right? Just like computers have sensors. We have sight, we have hearing, all those different senses that we have. You can kind of attach a lot of those to computers as well as sensors. And then we're perceiving our environment, and then we're making choices, right? As humans, we're making choices all the time, like when we're driving, like trying to swerve around objects and stuff. And we have goals. We're trying to achieve some goal that has either been programmed into us by ourselves or our parents or something, who knows. But it's a very utilitarian idea, right? That's kind of what we're giving to a machine. That same idea, having them perceive their environment through sensors, like you can give them little webcams, little radars and things, and programming the ability for them to make choices. They can walk around and giving them a goal, programming in a goal that they would like to have one day. Okay, so super nice. Noah would love it. And artificial intelligence is a very broad field. So there's a bunch of different little sub areas of AI. I would count robotics as that. Like, you've seen all the weird Christmas videos of these weird looking robots. That's like Boston Dynamics. They have a lot of money to do weird stuff like that. So I encourage you to look them up. Robotics is one. All right, we're gonna make a machine to help us build a house or something like that. That's important. You also have machine learning. I consider that to be a subfield of artificial intelligence, where you have things like, okay, you have a camera that's doing face recognition, or your phone is unlocking itself with face recognition, stuff like that. Or just even machine learning powers ChatGPT and all that. So producing images, producing text, that's all machine learning, that's artificial intelligence. And the backbone of all those cool things that have popped up recently is something called neural networks. Okay, and so have we heard of that word, neural networks, before? I will teach you what it means if you haven't, don't worry. But those are the backbone of pretty much every machine learning task these days. Those are the cool thing. We have enough processing power for it these days. But it's not a new concept. It's been around. They've just gotten really good now. And I would count statistics, because at the end of the day, maybe some of you want to be data scientists or something. All artificial intelligence is, most of the time, is glorified statistics. It's just like a rebranding of the idea of statistics. It really is a lot of the time. So just using statistical methods, shoving that in statistical tests and things inside of a computer or a robot, that produces intelligence a lot of the time, right? To our own definition of intelligence. Okay, so I hope that makes a little bit of sense, and I have some examples for us now. So let's look at some examples of artificial intelligence. I would say the first one that came on the scene that was a big deal for a lot of people, maybe you guys were still very small children at the time, was digital cameras. Used to, and you probably still do, used to buy separate things to take pictures, right? Digital cameras. And on the screen, they had digital displays on the camera screen. Didn't really look through it anymore. They drew little boxes around people's faces, and they could tell if somebody blinked. Right? Have any of us interacted with an old digital camera that did that? That was the coolest thing back in the day, and that's the first piece of, I would say, artificial intelligence, machine learning software that existed. It was able to notice hey, here's a person, and here are their eyes. It's able to tell here are their faces. It has to find the people, of course, and then it's able to notice okay, here are the eyes on the people. Let me look at them. I can tell if they're open or not. Okay, so that's blink detection. It is machine learning at the end of the day. It's a simple form of machine learning. All right, we taught somehow a computer to notice where the faces are and where the eyes are within those faces, and like what is the difference between an open eye and a closed eye. And then it will tell you like, oh, you should probably retake that picture of one of the people. Here's a box around them, they blinked. Which is really nice, right? Really useful. And it became cool, easy enough to program to shove it into a very small device back in the day. Okay, so yeah, it's a machine learning technique, and now I need to tell you like what does machine learning mean? What's the difference between that and AI? It's really just like the way that you create it. I would say like the process, the recipe is the main difference. Like here's what it means to make a machine learn, to use machine learning to like create a task. Okay. To solve a problem, to do a task. So here are the steps. If you want to do machine learning, you must do these things. Okay. So the first step is usually you'd like to train your machine learning model. We say that's what it's called. Your program is called a model in the machine learning realm. You're going to make a giant set of training data, which means for our blink detection, what they did is they got a bunch of pictures. Okay. A bunch of pictures of people and not people. All right. So you're going to do the following. You're going to make a bunch of pictures, like you're going to feed a lot of pictures to your machine learning software, and we'll get into that in a second. But like usually the first step is you need a lot of data somehow, okay, to train your software, okay. And so you're going to provide a bunch of pictures of people with their eyes open. So like eyes open. We're talking thousands, maybe even tens of thousands of pictures like this. Eyes open, eyes closed, right? And you've labeled them. So like, no, there's no guessing. Like, okay, this is a picture with somebody with their eyes open. This is a picture of somebody with their eyes closed. And you got thousands of those. All right. You also need pictures of, let's see. So you're going to label it like that, with like eyes open, eyes closed. And yeah, like we're trying to notice faces, for example. And so we're also going to give it a bunch of pictures of people with just faces. Maybe like their head is turned, so their eyes aren't even in the picture. Like that's a thing. And also non-faces, because you don't want it to just start guessing and hallucinating like we've heard before. Right? So you're going to give it a bunch of pictures of faces, sure. And then also you're going to give it a bunch of pictures of non-faces. Like here are some airplanes. Don't have it go thinking like there's a face somewhere in a picture of an airplane, right? You have to train it to not do that as well. So just a bunch of labeled pictures, okay? Eyes open, eyes closed. There are no eyes in this picture, but there is a head. This is like the back of somebody's head. There are no eyes at all in this picture. There are no faces at all in this picture. Like label it like that, okay? And then step 2 is kind of the magic. There are a bunch of algorithms that take that data and somehow learn from it. All right? That's something I can't really tell you too much about. But I'll give you several examples, right? You're going to what's called train your model, like you have it work really hard, go to the gym. You're training it on these pieces of training data, right? You're training a little program, which is called a model in machine learning lingo, using some sort of technique, all right? And one technique that is very popular is called using a neural network, okay? And yeah, you kind of let that take over and start learning. Whatever method it needs to learn. So yeah, you have statistical methods, you have these things called neural networks, which just briefly, what they do is they kind of model inside of a computer what a human brain might do. And so hopefully we've kind of heard a little bit of what brains do, taking like a biology class, right? So in a brain, you've got a bunch of neurons and synapses and whatever. But what neural networks do is you have a bunch of little programming things now. This is inside of a computer called little virtual neurons. And so what a neural network is we're hooking up a bunch of virtual neurons to move information around, and those pieces of information are just numbers. Like so you feed in numbers, like, and like those, like that activates these neurons and they can learn from each other. That's as much as I want to go into it. Like, okay, maybe that sends some numbers that way. This neuron really doesn't like whatever you gave it, so it sends a negative number outside of it, and then like the final answer is some other number, okay? And maybe that number means, oh, I saw a person's face and their eyes were open. So like you've hooked together a bunch of numbers, essentially, like neurons, and you can shove information in between each other. All right, I'll give you more examples of what that kind of means later, but like that's a good start. That's what we're doing to model a brain inside of a computer, all right? And so we're just like, eventually, like you start off your random neural network with a bunch of those things, those random neurons like firing off to each other. Like you initialize it randomly. And usually that means like it's hallucinating all over the place. It's like, all right, you show me a picture of a plane, like it is convinced at the start, like there's a picture, like there's 10 people in that picture and all their eyes are open or something completely wrong. And eventually, like your technique, your neural network technique, it's able to learn from its mistakes. All right, over time it starts getting better and better. It figures out like what went wrong from the previous runs, why it was wrong, and it helps itself get better and better and better at your training data. Okay. So the more training data you have, the better. And that's kind of the hardest part, honestly, to get a bunch of training data. So, and then finally, once you have your model, which is just another name for your machine learning program, right? Trained and ready on your training data, and it's doing pretty well. What you do is you test it on another piece of data, a piece of data that you haven't shown to it before, because maybe it's just memorizing, right? It's memorizing this exact picture, this exact picture. You don't want that. You want to give it something it's never seen before to prove to you that it's actually learned something. Yeah, so you test it on something it's never seen before, a separate set of labeled data, so you know the right answer still. And you just make sure like it's still doing well there. Make sure it's getting right, getting most of the things right there. And those are the steps. That's how you do machine learning. There's a lot of magic, especially in step 2, which I will try to make a little less magical. But like that's pretty much it. All right, it's pretty cool. And honestly, step 1 is the hardest part, to be completely frank with you. It's very hard usually to get a lot of good labeled training data. And so now you know why, like, you're able to post a bunch of pictures to Instagram for free. Why Google Photos used to be free, and like we're going to store every single image you want to put on me. But then they stopped making it free, sadly. Like, everybody was trying to get a bunch of pictures so that they can train their artificial intelligence. Like, Google was trying to do it, Facebook was trying to do it, and now it's pretty good. So now they're charging you for things, which is fun. Yeah, that's one of the reasons it was free. Yeah, so that you gave them permission in your terms of service, right, for all that, which is wild to think about. But yeah, a lot of this is being done ChatGPT these days. Most machine learning things that are really cool to us that we've heard about are using these virtual brains, these neural networks, just a bunch of neurons sending numbers to each other, essentially. And I want to show you a little bit more of that. And so let's talk about it. So first, let's go to this website if you've never seen it before. I hope it still exists. It's called crayon.com, C-R-A-A-I, right? Instead of however you normally spell a crayon. There's AI in there secretly. So just if you've never done this before, I'm forcing you to do it. So go play around for a minute or two. Feel free to post to Discord some cool things. But this is just image generation. You'd be like, all right, a cat sniffing a flower with a rainbow in the background. And you just click draw, and like it'll go off and be happy. And yeah, so it's called crayon.com. Just like give it something. Your favorite idea is taking text to images, okay? And while it's working, what do you think this website was trained on? Because it was trained in some way, wasn't it? It was given a bunch of data somehow. What kind of data do you think it was given to like figure out how to take this and draw stuff from it? Well, just like the picture of people, right, with their faces and stuff, and like boxes around them. Like that was your training data. If you wanted to learn how to detect faces, you want to learn how to take pictures or text to pictures. You just gave a bunch of pictures, right, with a bunch of descriptions of those pictures. And it learned like what it meant to be a cat because you got a bunch of pictures with descriptions that like there's the word cat in that picture. It learned like English essentially. It learned what a flower is because you gave it a bunch of pictures of things, like pictures labeled with descriptions that included the word flower. Like, okay, this must be what it means to be a flower. And just with enough examples, it learns what it means to be a flower and how to create that out of images. And so look at it, it's so cute. It makes sometimes animated version, lifelike version, but sometimes it's still a little trippy, right? Like the eyes of the cat are a little in a weird place. But like you could draw over this and like make it nice, but like it's giving you ideas. So that's what it was trained on. Does that make sense? Like it was trained, if you want to be able to do this, it's taken a bunch of like pictures and descriptions of those pictures. And it learned English based on that. And it learns like, okay, this must be what a flower means, because I see the same idea of like the stuff on a stem or whatever in all these pictures. Like the AI noticed that, the neural network noticed that. That's really cool. All right. So yeah, I hope you also got some cool stuff. But like here are some other things that people have made before. And you can tell it how to draw it, like draw it like a drawing, draw it like an actual photo or whatever. I don't know. But yeah, play around with that if you'd like. And then the next place I want you to go to, this is the more important place. This is actually going to teach you what a neural network is. It's called playground.tensorflow.org, please. Please go there. And this is what I want you to do now. So here, once you get here, it's called playground.tensorflow.org. This is actually going to teach you what neural networks are all about. Why numbers and shoving around numbers, it does something good. Okay. So again, the idea of a neural network is you somehow feed in inputs. Like maybe your inputs are all the pixels of an image or something, or it's like English text. And then you can create some like web of neurons in a virtual brain, essentially. And like it's feeding things around and like shoving things to other layers of the neural network. And eventually there's an output that is another number, or maybe, and then you can interpret that number as a pixel color or something. But like essentially you're giving it numbers as input. Like these are pixel values, places on a grid or something. And like the next nodes, the next neurons in this neural network are taking the inputs, like the 1 and the 2, and like performing some function on top of those, like doing, maybe like they're adding the numbers and like doing something special with them. And like this one was just doing something special with the 2.0 because it's only getting one thing. And that's pretty much all it's doing. It's like adding together what you got, what you gave it before, and like doing something special with it, and using that and propagating that information. Okay, that's pretty much what a neural network is. And here is a way to play around. Here's some data. All right, you can click different ones. I'll do this one first. But here's some data, and here are different things that you can give as input to your neural network. Essentially, what we want to do, like the goal of this particular website, is something simple. What it's trying to do is differentiate between the blue dots and the orange dots for different sets of data. So like, let's keep it this one. We would like to learn a way to differentiate the orange dots from the blue dots. And then you can imagine this will scale to image generation one day. But like you can give it input. Here's what, you can give it multiple inputs. You don't have to give it just these. And then we'll eventually tell it to learn. So here is what x1 means is it's what we're giving as input is just like an uncolored dot. Like we give it a dot like this. We're giving it the coordinates of this dot or something. It's like, go and guess. Was it blue or was it orange? We're giving it a coordinate way out here. Like, hey, learn, guess. Now, should this dot, if we place one right here, should it be blue or orange? Okay, that's what we're training it on. And so, yeah, we'd like to learn the difference between the blue dots and the orange dots, and we can give it different inputs. So x1 means the x coordinate of the dot. x2 means the y coordinate of a dot. We can use those, like those are kind of important, right? You can get rid of one of those, but it's not going to learn as well. Does that make sense? x12 means, what does that mean? Let me think about that for a second. x1 times x2, like that one makes sense. I forget what x12 means and x22 means. Oh no, sorry, it's because they're using subscripts and superscripts at once. This means squared. This is the x coordinate is x1 squared. x2 is the y coordinate. There it is, squaring it. Their multiplication, the sign of the x coordinate and the sign of the y coordinate. You can feed those all in as inputs to your neural network, and you can give it a bunch of layers so that it learns things, and they can have different neurons, right? But all it's doing is it's figuring out, like, in your output layer, eventually, like, the final thing is blue or orange, right? And so maybe your last number that you give out is like either a positive number and a negative number. And if it's positive, it'll think blue. If it's negative, it thinks orange. But like, if you give it enough layers and enough input, and you click play, it will try to learn. Like, it'll try and build up knowledge within itself. and it will eventually learn to differentiate the blue from the orange. Do you see that? That's what it's learning. And so essentially, you can kind of see how it really is just like doing some addition and like messing with stuff, because like you can see like this is the x coordinate. It's learning from the x coordinate and the y coordinate, and eventually you can pause it when it's happy. Like it did so well, it discovered this little blob that separated them. You see that? And so you can kind of see how it's like feeding numbers. It's giving more weight to more important things. Like this neuron is like, it really liked the x coordinate. There was a high weight there that it took. It didn't really like the y coordinate too much there. But this neuron kind of took an even amount of both. And eventually you see how they're like, it's learning lines, essentially. It's learning the addition of x and y coordinates. And then over here, like you're adding lines together, and you're suddenly making some, it's learning little places. It's learning more blobby looking things. And apparently, like these ones down here were the really important ones. Like these took these guys. These are really important things, and like it learned from them. It learned how to section off things. Now it's starting to learn like the difference, like circular things. Does that make sense? That's the goal. And so like try it. Try to learn how to separate the orange and blue dots using just coordinates for the other data sets. And you can add a million hidden layers and a million neurons all over the place if you want to. And you click play to learn. All right. So just try that. See if you can get it to learn the difference, because that's what a neural network is doing. It's just learning math, essentially math formulas. Like which inputs were most important and how can I jumble them together to figure out what's what. My challenge for you, though, is use the minimum amount of neurons and hidden layers even, because the more you have, the more money it costs to run your model all day long. Like, how can you learn the difference between those orange dots and those blue dots? If somebody just gave you the coordinates, some special way, maybe square them, you took the sign. They just gave you like the coordinates of one font. Should be blue dots. How could you learn that from your training data? What tells you? Take like a minute or two to play around, keep going, and then I will show you what I think are the best ways to think about this, because there is kind of a science to it. Let's see if you can get this in the smallest number of neurons, smallest number of inputs too. Please shout out if this does not make enough sense. That's kind of what's going on. Somebody's giving you a coordinate of a dot, and it's your job to learn. Should it be blue dot or orange dot? Go back to this one. Alright, that's my timer. Let me show you the secrets. And you can kind of see, like, at the start, like, it's just a huge mess on the right in the picture. Like, it doesn't know where anything is. But eventually it learns. It learns better and better. But, yeah, I'm here to tell you, like, for this first data set, this is overkill. Like, this is way too big of a bill for your machine learning usage. Like, you don't need this many hidden layers, because, like, what's the difference between the blue dots and the orange dots? What should we draw in between them? This is like a perfect circle, right? So do we remember what the equation of a circle is? How would you graph a circle? What's the equation of like a circle with a radius 1? Remember? That's like the area of the circle. Like, how would you graph it? It's going to be x squared plus y squared equals r squared. Remember that? Maybe it's been a while. But this is the equation that we want to learn, right? And I'm telling you that if you have a bunch of neurons hooked up, they will add together their inputs and then do something weird with them. So honestly, all I need as input to discover this, like, learn a circle to, like, get rid of these guys is, like, remove every single layer. Like, there's still an output layer, of course, and only give it x squared and y squared. It will add them together and learn the radius squared. Does that make sense? Boop. Immediately, it learned a perfect circle, because that's all it can learn. And, like, that saved your boss a whole bunch of money. So there is virtue in learning, right? Learning, like, about machine learning. Because at the end of the day, yes, you could just, like, max out the number of hidden layers and max out the number of neurons. But, like, that's a huge waste of computational power. Okay, there are tricks to it that you can learn. So that's kind of cool. So that's probably the best way to do that one. With the same idea in mind, like, what are the best inputs to discover the difference between the blue dots and the orange dots here? Yeah. Mm-hmm. Yeah. So, like, notice that, like, is these, like, quadrants 1 and 3, right? Quadrants 1 and 3 are blue, and quadrants 2 and 4 are orange. What's the difference between the points in those quadrants? If you think about it really hard, it's like these are both positive coordinates, right? In the blue here, they're both negative coordinates. And here they've got 1 negative, 1 positive coordinate. See that? And so, like, maybe the easiest way, definitely the easiest way to notice, like, which of these two quadrants you're in, two sections you're in, is to multiply the x and the y coordinates together. So you just need that one input, and it will learn the difference there. See that? Just gonna, all right, give as input the multiplication of the x and y coordinates. Just like it immediately learns the dividing line there, which is really cool to think about. And so that's another way to save you money. This one, what's the difference between the orange dots and the blue dots? Like, what would section them off easily? You got a few options, right? You can draw a circle around just one and not the other. You could, I think the easiest way to do it in my mind would be just draw a line. A line would separate them. It's like, what's the equation of a line? Y equals mx plus b. So you got y and x. Add them together essentially, and, like, learn the radius, or not the radius, but the slope. And so there it goes. You only need those two inputs and one output neuron, as usual. And they're both giving this, like, apparently it learned that the y coordinate was slightly more useful than the x coordinate for some reason. But yeah, that's kind of the idea there. For the swirl, like, this is you can't really make an equation of different parts of a swirl very easily, so you kind of just have to go all out for this one. Like, max them all out, try everything. I guess sine and it has to do with turning, but still, it's a non-linear idea. So, like, just give it a bunch of neurons, and eventually it'll figure it out. And that's probably the best way to do that. Because it's ugly, but sometimes, like, there are tricks, and you can do better than this, but other times, it's just got to figure it out with some weird-looking input. And so you can imagine, like, there are harder problems to give to this, like image generation, text completion, and you kind of just have to shove a bunch of neurons at the problem at that point. Excuse me. Thank you. But yeah, eventually it'll get better. Like, it's getting better and better. You can see it's called loss. Like, how bad is it doing right now? It's called loss. It looks like it's converging, and it's doing pretty well. pretty well. But yeah, you can see like it's hard to learn to swirl. But hopefully that helps you understand like what's going on deep down. But yeah, that's neural networks. In a nutshell, that's what powers modern day AI. I encourage you to look more into it if you're interested. But yeah, that gives you everything. All right, so let's just talk about a few examples and that'll be it. So yeah, one use of machine learning and artificial intelligence is like robots to do things that humans aren't as good at doing, or at least as quick at doing. So machines are super good at like doing the same thing over and over again. So like if you're building a car, it's nice to just build a machine to help you build that car because it can just like always put the right things in the right spots, right? It'll never mess up unless like it actually like catastrophically fails. But like as long as you keep oiling it or something, it won't fail too often, okay? And then they'll work much faster and more precisely than a human on like a supply line could have done, which is it's kicking humans out of the process, which is maybe unfortunate because we're losing jobs there. But yeah, to make a factory robot, it's going to cost a lot of money up front because you have to like program exactly like how to do these little pieces. But like the second it's programmed and you've made it, like it just takes electricity. You never have to give it a salary at that point, which is, I don't know, capitalism is weird like that, but like that's the thing that's important, and that is machine learning. That's artificial intelligence. Another fun thing was, I don't know if we've seen this, it's been like a decade or two now since this happened, but a really cool thing that shocked the world was this Watson supercomputer that played Jeopardy. Have we heard of that? So yeah, go look it up on YouTube. This is like a mind-blowing moment for people like a decade or two ago. But this was like the first time people were like, oh, a computer is really thinking. Because like to play Jeopardy, you have to think, right? You have to look up some ideas in your mind, right? So Watson is it's a supercomputer. It was made by IBM starting in 2005, but they kept iterating on it. And what it does is it uses a bunch of cool machine learning, artificial intelligence ideas. It uses natural language processing to like read and understand the question that's being asked of all the contestants on Jeopardy. And then it's like figuring out what that question means. It's parsing English, right? And trying to answer it using a giant database of information. And so like it went on Jeopardy and it won Jeopardy eventually. It was just so fast at answering the questions correctly. And it had like an entire copy of Wikipedia inside of it. For example, that's how it was good. But like it was, they brought it on and they gave, like they had it try to play against a bunch of people who are really good at Jeopardy. And like it just kept beating them, so it's really cool. But yeah, here's kind of what happened. I had to take the English sentence and like parse it, like figure out where's the subject, where's the verb, like what is this question asking, and then it has to like cross-reference its database. Like, okay, now I know what it's asking. Like, what are my possible answers? Got to figure out answers, and maybe it has a bunch of ideas. Like, it could be answer 1, it could be answer 2, it could be answer 3, with a bunch of different probabilities. 91% chance it's answer 1. I'm 85% confident it's answer 2. Maybe like 5% confident it's answer 3 or something. And then we'll just like pick the one. If it's above a threshold, we'll pick that one. But that's what a computer had to do, right? We've been able to program the computer to break down text and like understand it and answer questions. And like this was a decade at most, right? At least before ChatGPT. So like this was a huge deal to people like, oh, computers are getting smart and they can see it, which is fun. And then like a huge deal in the artificial intelligence field is like they all love to play chess and stuff. So like they're really like the pie in the sky dream for early artificial intelligence researchers back in the 60s and 70s was like, let's make a program that can play chess and beat a grandmaster. That was a huge idea and a cool thing for them, okay? And eventually they made this possible. It's been a while. Like it's not too surprising to us nowadays, but back then it was a huge deal. It was back in 1997 when, for the first time, a computer beat the current like world champion at chess. So it's very, very cool. And like what it has to do is like, all right, you need a lot of processing power for that because like it's got to like imagine like, okay, here's the current state of the game board. Where could we go from here? I could make this move, this move, this move, this move, this move. Like you got a bunch of options, right? And the board looks like this in that case. The board looks like this in that case, etc., right? Like all these different options for where the game could go from here. And then you got to go underneath that. Okay, if I make this move, my opponent might make this move, or this move, and the board might look like this. Like you have to have a bunch of different levels of thought, and like that kind of computation takes time. And eventually they got it down, and they figured it out. Okay, and it's very good, better than any human these days, chess software. But like it didn't used to be like that. Okay, and so yeah, Go is another game that I got really good at playing. And it's a harder game, so it took even longer to beat a world champion there, but like games like this are important for the artificial intelligence communities. And a cool thing to think about is like one easy way to learn, teach a computer how to play chess is you don't even need to give it any training data. You can just have it play itself, because like the rules of chess, you can program out the rules of chess, and you can just like have the computer keep playing itself, and it knows like eventually like what it took to win. Isn't that crazy? Because it knows the rules. You just have to keep making valid moves. Eventually it'll learn like what it means to win. It doesn't need any prior information. Just wild. All right, this is crazy to think about, in my opinion. It's really, really cool that we've come this far, and we're going to talk about that a whole lot more next time. But before we go, I want to release your next essay and then give you a good example. All right, so this is going to be a bigger essay. I give you 2 weeks to do it. It'll be 1,000 words. All right, that's your next essay. And I want you to read all of these directions. I won't have time to go through all of them, I don't think, but I'll do my best. Please read all the directions. I don't want you to lose points. There's a lot of requirements, okay? This one is about fallacies and finding them, okay? So what you're going to do is you're going to find 5 separate fallacies that somebody posted to social media, all right? So like go scour Facebook, go on Twitter or X or whatever it's called, go on the comments of YouTube videos or of Instagram posts by famous people or politicians. That usually helps. And go find people messing up in their arguments. There's a ton more fallacies than we talked about. Like there's a huge Wikipedia page. You can find any fallacy you want as long as you argue like why it was that fallacy, okay? But yeah, you don't have to pick CSCI related topics, but like here are some good ones that might be useful to search on, like to help you find things. But I want you to go on the internet, find people arguing, like go on Reddit or something. Look at the comments to political posts by news websites. I want you to find 5 separate fallacies that people make. Does that make sense? That's going to be your challenge. To go find them and argue why they were that fallacy. Okay? So that's what I want. So at least 1,000 words in the following way. Like introduction, conclusion as usual. But I want at least 5 separate paragraphs as meat in the middle, giving like you're quoting like a Twitter tweet. You're going on social media, you're quoting something that you found that has a fallacy in it, and then you're analyzing why it has a fallacy. All right? So remember to say its name. Like, this is a false dilemma fallacy. This is bad. And this is why it was that one. Does that make sense? That's what I want. Okay. I want you to find people making mistakes on the internet. Okay? Hopefully it won't be too hard to find. But that's your goal. And I do have one last requirement, because I know, like, people are mean to each other on the internet all the time. Everybody uses the ad hominem fallacy. So you're only allowed to find 2 ad hominem fallacies. You have to pick at least 3 other normal ones. Okay? But that's going to be your next essay. Find 5 fallacies and tell me why it was that specific kind of fallacy. This was a false dilemma. This was a straw man. Does that make sense? All right? So make sure to read these directions. I want to make sure you all get credit. But you can quote any post. It does not have to be about computer science. It can be about politics. Like, that's an easy one to find. But yeah, that's what I want. All right, and here's like an example of that. Here's an example for your essay. All right, so there's a ton on the internet. So this is back from Twitter. Here's a straw man fallacy, I would say. So here is a tweet. It's like, all right, a couple years ago, Kamala Harris posted this, like on International Women's Day. Like, I just want to honor the women who have been helping out, especially in this was during the pandemic. And then Dave here posted as a response, just I would like to thank the women who for over a year have gone to work, often risking their health to nourish and protect us. All these nice people. Picking out the women, okay? Like on International Women's Day. And then Dave responds, just the women? Guess that would be typical of you. I thank all who risked their lives for others. Okay? Risk life for others. And like what I would do, if this was me in my essay, I would say, all right, here's the setup. quote these 2 tweets, and say that Dave's response has a straw man fallacy in it because he's putting words into the vice president's mouth. He is trying to claim that the vice president is not trying to thank everybody, only thanking the women only, when in reality she's talking about women because it's International Women's Day. She doesn't hate men or something. Does that make sense? That is a fallacy. So, and you'd like, that's a straw man fallacy, and here's why. So I want to see 5 of those from you guys. Does that make sense? All right. I know there's a lot to think about, but that if you read it and you look at that example enough, it should make sense. But yeah, I think that's everything that I wanted to say. If we're good, you can leave a whole minute early. Any last questions about anything? Yeah, and also remember to say the name of the fallacy. Don't just be like, this is a fallacy and move on. Tell me it's a straw man fallacy. It's an ad hominem fallacy. Okay? Oh, that's fine. No, yeah, that's totally okay. As long as you analyze it and tell me why it's that fallacy, I'm happy.